morning. I'm Carmen Bax. I work at the Olfatometric Lab of the Polytechnic of Milano, and today I will present our topic will be about the recent advances in the optimization of inosis for the environmental odor monitoring, focusing on the compensation of drift and utility effects. The Olfatometric Lab has been already widely presented this morning, but we focus on all of the cutting-edge technologies for the odor monitoring, combining different type of measurements. Today, I will focus on the presentation of this big group of working on the INOS development at the Polytechnic of Milano by involving not only people working directly at the Olfatometric Lab, but also involving the another laboratory of the Politecnico, the TechRes Lab, who provides the background and the competencies in the developing of hardware and electronic solutions. We are together working on facing the open challenges associated to the use of the IOMs or INOSIS for the different types of application, among which the environmental odor monitoring. And today I will focus specifically on two big tasks of these slides, which are the compensation of interferences that had been already discussed this morning, and on the compensation of drift, because as everyone I think is attending this conference knows that the signals provided by gas sensors experience this drift over time that causes that has some negative consequences on the signals and on the outputs that this type of instruments can provide for the environmental monitoring. The combination of drift over time, that is in the term of these signal deviations of these response deviation over time, combined with the competitive absorption of water on the sensor active surface, causes as a consequence a drop of the odor classification and quantification performances over time that is important to be corrected in order to ensure also over prolonged monitoring period stable and reliable outcomes provided by this type of instruments. We are working on this type of topics since many years, and we focused and we presented our results relevant to different types of applications in our recent and less recent publications. We try to implement software compensations both for the correction of drift effects on sensor responses, and here in these slides I reported the improvement on the accuracy, on the classification accuracy of the instrument that we obtain after applying the correction of drift effects on the sensor signals by considering the training data sets collected over 3 years at Ellensfield that we monitored for this specific application. While on the right side of the slides, I reported the compensation effects, the results of the compensation that we implemented for correcting the humidity changes that the sensor experience over the monitoring when it was installed at the fence line of the waste treatment plant. And we decided in that case to implement a dynamic baseline compensation of the sensor signal, considering the changes of the absolute humidity of the sample that the gas sensors were analyzed. And if you compare the accuracy obtained before, without, and with the correction, you can see that it's worth to improve, to compensate for for such interferences in order to ensure the reliability of such outcomes. However, by deeper analyzing and investigating this topic, we discovered that the application of this type of compensation required an update of the model, a correction month by month, because the dynamic baseline compensation was not so much stable over prolonged monitoring periods. And moreover, we decided to improve the mathematics behind the choice of the polynomial regression for the compensation, because there is no real physical meaning behind the selection of this type of model. For this reason, today I will focus on the results of this further investigation that we are carried out by considering as a case study the fence line monitoring that we are performing at a waste treatment plant. We are using two instruments that are installed at the fence line of the plant, and the network of instruments also include a meteorological station whose signal are used in order to are combined with the outcomes that are provided by the instruments. The challenge that we wanted to figure out within this project is the simultaneous compensation of the humidity and drift effect, with the purpose of training and use the IOMs for the real-time identification of odor presence, recognition of the source causing the odor event, and also provide an estimate of the odor concentration at the fence line. In these slides, I reported a plot showing how the sensor response, how the response of one sensor of the array that we are using is affected by the changes in the moisture content of the sample. Specifically, here we report on the y-axis the resistance of the metal oxide semiconductor sensors versus the absolute humidity of the air that the sensor was analyzing. And as expected, the resistance of the sensor decreases with the increase of the absolute humidity. The deeper investigation of this plot highlights also the problem of drift, because we see a shift in the baseline of the sensors occurring as the time passes, so as the aging of the sensors that we were using. This enabled the efficacy of the dynamic polynomial model that we implemented for compensating the humidity changes, because we needed to update, as I mentioned before, this, the coefficient of the model month by month. For this reason, we tried to implement an alternative. We decided to use the orthogonal signal correction model as a first step in order to compensate for time effects, so to compensate drift. And then we use the correct data in order to implement a single regression model. We try to evaluate different types of mathematical models for implementing this baseline compensation by comparing exponential model, power law models, and we ended up with the implementation of a dynamic baseline compensation model for correcting the effects of the moisture changes on the sensor response. Since the changes in the absolute humidity of the air that the sensor exposed to over the monitoring periods is something out of the control of the user of the IOMs. In order to evaluate the efficacy of these novel approaches for compensating simultaneously the drift and the changes in the moisture content, we consider the field data acquired by the sensors over by the IOMs over the monitoring period. We consider 1 year of monitoring starting in March 2024 and until March 2025, and we decided to consider like a figure of merit the accuracy, the performance of the classification model that we implemented for that application, for that monitoring, to discriminate between the principal odor classes of the plant. That is a waste treatment plant, and so we implement a classification model to distinguish the odor class air, which is representative for the neutral condition of the monitoring, so no odor presence at the fence line, and to recognize, in the case of the odor presence, the provenance of the odor belonging to the biogas odor sources and the organic treatment. We included in the biogas group all the sources mentioning the potential leaks of biogas from the biodigesters to the upgrading sections of the biogas, because the plant is a plant converting the organic fraction of wastes into biomethane. And we considered within the organic class all the sources associated to the storage, the collection, and the pretreatment of the waste prior the biodigestions aimed at the production of biomethane. We assessed the performance of the model by considering a completely independent data set from the training, including 63 samples. Focusing on this step of the data pretreatment, which is the topic of this talk, we compare the old data pretreatment approach, which was based on the dynamic baseline compensation with polynomial regression model, with the new approach proposed that combines the orthogonal signal correction for correcting drift plus a dynamic baseline compensation based in this case on an exponential power law models. The results that we obtained on the 63 samples completely unseen by the model show that the system is capable to, the correction allows us to improve the performance of the classification models, even if we were using age sensors. And so these results makes us happy because we were able to implement a robust version for the software compensation of interferences that are that cannot be managed in other ways during the monitoring periods. Moreover, we implemented the section providing a real-time output provided by the IOMs installed defense line of the instrument directly in the control systems of the plant. We implemented a section with the contribution, of course, of the engineers working at the plant. We were able to implement the control room of the plant, showing also the real-time outputs that the two instruments installed at defense line provides over the monitoring periods. The system, we decided to show the information about the odor class detected by the two IOMs, plus the estimation of the odor concentration provided. The results that we achieved within this project are very satisfactory, not only from a scientific point of view, because we were able to implement and verify the robustness and the reliability of the IOM's outcomes provided during the monitoring periods, but we also received a very positive feedback from the plant managers, because the network that we realized at the plant helped them in identifying anomalies working conditions of their plant. They reported to us that one day they started receiving frequent detection of biogas by one of the two IOMs installed at defense line. So they performed an inspection directly at the plant, and they discovered the they discovered the occurrence of fugitive emissions from one of the two biodigesters. And thanks to this alarm provided by the IOMs, they were able to manage in a very short time period, and they can intervene with maintenance activities. Before concluding, I want to invite all of you who are interested in the topic of environmental odor monitoring and IOMs and electronic noise on behalf of ISOCS to the next ISO conference 2026, which will be held in China in May from the 17th till to the 20th of May. So, I hope that someone of you, or all of you, will attend this conference. And I remind you that the submission of abstract, the call for abstract, is now open, and the deadline is set at on the 5th January 2026. Thank you all for the attention, and I'm available for questions or curiosities.
Thank you, Carmen, for your contribution on the optimization of the electronic noise.